Conference will now be recorded.
So I'm just going to repeat that part of it so it gets into the recording. Mu and sigma for a population, we're almost never going to know. So our only window into mu and sigma for the population, the true population mean, true standard deviation or variability of population, is our sample, the sample we take from that population. So we can choose the sample size based on the resources that we have, the time we have. And then from that sample, we can determine the average for that sample. We call that X bar, right? And we can determine the variability for the people in that sample. We call that S, or just standard deviation, or S, right? So the thing is that X bar approximates the population mean. It's not the same as population mean. In fact, we'll never know how close it is because we'll never know what the population mean is. And the standard deviation of variability of sample, well, since you're randomly sampling people in that population, the variability in the sample is going to mimic the variability in the population as well. So it's going to approximate it as well. It's going to approximate sigma. So this is what we have to work with, right? Problem is that we need to know how precisely we know this in a situation where we're never actually going to know what the mean and standard deviation is. So we need some other way to nail this down. And that's what we've been working on for the last week or two, this idea of confidence intervals instead of being able to predict how well we actually know the population mean. You know, we look for a range within which we have some confidence that we'll actually capture the population mean. And this works because we understand how variability in sample means takes place. That's where the central limit theorem comes in. In other words, from this data that we have now, we can say to ourselves, let's say the sample size was 100, right? From this information that we have now, we can say that the variability in repeated samples of size 100, could have been size 10, could have been size 25, 30, whatever. The variability in that sample size, which whatever it is equal to sigma over the square root of the sample size. Well, again, we're in a situation where we rarely know what sigma is. So instead, we use the best substitute we have for it, the standard deviation of the sample over the square root of n. Right? So this tells us how variable samples are within this sample, the population that this sample was drawn from. So if we repeatedly take these samples over and over and over again and calculate the means, since we know the variability of what the variability is likely to be in repeated samples from this population based on the best guess we have at the mean and the best guess we have at the standard deviation of the population, since we know that, we can make predictions about how variable the sample means are going to be and how far from the actual mean we might be likely to be. And that's where our confidence interval comes in. Our confidence interval allows us to predict that our sample mean plus or minus some value, which is going to be z or t, number of standard deviations. Either one. The z represents a number of standard deviations away from the mean x bar, right? Number of standard deviations or standard errors away, because we're talking about a sample, it's standard errors in this case. And t, I use z when I have a very large sample size, right? Why? Because when I have a very large sample size, say over 100, then I have a lot of confidence about how variable the population really is. So I relax a little bit and say, gee, over 100, I might just use one z. And for 95% confidence interval, we've learned that that's equal to 1.96. Approximately 2 standard deviations below the mean, and 2 standard deviations above the mean. 95% of the sample means are going to fall. So when I have a small sample size, you know, the variability, I don't have as good a handle on the variability. I have some extra baggage there in terms of the amount of error I could be introducing by not knowing what sigma really is when I substitute S for sigma. So in that case, instead of using 1.96, we use the t value. And the value that we use, the critical value of t that we use, I'm going to use that term a little early here. The critical value of t that we use is going to be determined by how big the sample size is. So if the sample size is small, that might be as big as, say, 3.5. So in other words, instead of 1.96, I got to use 3.5. Well, if I'm going to add and subtract something that I'm going to multiply 1.96 to versus 3.5, you can see that interval is going to be wider. I'm making up for my uncertainty by making my interval wider. So for a sample size of say 5, I'm guessing at this. Maybe it's a 4, maybe it's 3.5. For a sample size of 20, it might be 2.3. For a sample size of 50, it might be 2.0. For a sample size of 100, it might be 1.98. Well, look at this. We have such a good handle. We have such confidence. Once we get to 100, we're very close to that 1.96 that we might have used. Is it wrong to use the 1.96 for a sample size of 100? No, in fact, it's more right than it is to use 1.96. It's just that once you get that high, as a convenience, a lot of people just use that value, 1.96. Also, if you have a problem where they tell you what sigma is, then you can just use sigma over the square root of n, and you can always, no matter what sample size is, you can use 1.96. For the most part, though, when we're doing real work, we're using the t-value, unless the sample is very large. SPSS always uses the t-value, even if the sample size is 9,999. Right? No matter how big it is, it's going to calculate it using the t-value because it's got it built. It has the calculation built into it, and it's going to be more precise. Okay. Now it's going to be number of standard deviations, the standard errors in the case of samples, times the standard error itself. In other words, if the standard error is 10, then 2 times the standard error, we're going to be adding and subtracting approximately 20 to X bar, our approximation of the mean. And what does that give us? That gives us a range of numbers. That gives us a range of, say, 80 to 120, right? If the mean is 100, say it gives us 80 to 120, right? That 80 to 120 represents a range within which we're 95% confident that the true population mean falls within. So we still don't know what mu is, but now at least we have a range within which we can be confident that we could say that it's in that range. Does that mean we're sure? No, actually, it means that there's 5% chance that doesn't fall in that range. That in fact it's outside of that range, either lower or higher than that value. So we still have that issue. And if we're really concerned about that, we could create a 99% confidence interval where we use a different z and t. Z would be 2.58, and t would be determined by the sample size again in the chart. Okay, and if we're willing to be 90% confident, have less confidence we capture it, then our z would be 1.64, and our t again would be in our table. We would look it up, but you can see they would both be narrower or wider, to make meet the confidence interval that we're interested in. So this is pretty interesting, except now, how are we going to apply this? Okay, so one of the ways we can apply it is I can say to you that I have a population where I know what mu is, population 2. Population 2, mu is known to be 70. So if my result for my 95% confidence interval is 80 to 120, I can say to myself, well, gee, X bar is over here in the middle, it's 100, and the bottom of 95% confidence interval is 80, and the top is 120. Okay, I can say to myself, well, 70 is if the mu for the population I'm interested in, mu1, right, is between 80 and 120 with 95% certainty, right? Well, then I can say I'm 95% sure it's different than 70. It's different than the population mean for this other group. Okay, but if the mu was equal to, say, 85, could you still say that? No, you couldn't say that anymore, because the mu that you know could be the same as mu1. Mu2 could be the same as mu1 because it's within that 95% confidence interval. We don't know if it's bigger or smaller or anything like that. All we can say is that I can't be 95% sure it's different because it's within the range that I have 95% confidence that mu1 falls in. Is that clear to you guys? Make sense to you? If you're sure, if you were to do a survey and guess my age, right, and the 95% confidence interval came out to 30 to 50. First of all, I'm making that number up, right? 30 to 50. And you said, oh, well, the average for all professors at Hunter is 28, right? You know that with 95% confidence, my age is 30 to 50. The average for everybody is all Hunter adjuncts is 28. So you're 95% sure I'm older than the average. My age is older than the average, younger, whatever, older than the average for the rest of the group. But if it turns out that that mean is like the 35, well, then you're within the confidence range for my age, right? So you can't say with 95% certain that the average age for everybody is different than the average age of my survey, right?
Okay, so the average age is 35.
Yeah, let me rephrase that. Let me put that another way. Let's say that my age, let's say my age is 50, right? So you want to know if if the average age for all Hunter adjuncts is different than my age, right? So you would go, you could have two choices. You could survey every Hunter adjunct. There's probably too many of them to do that practically. So you could randomly select, say, 25 of them. And you could say that, oh, the average age for Hunter adjuncts is, let's say it comes out to 55, right? The 95% confidence interval is 51 to 59. Now, my age, you know, is 50. It's a known, right? So can you say that my age is different than the average for the rest of the adjuncts? Well, you can, because my age is outside of the 95% confidence interval. Can you say it for sure? No. But you can say with 95% certainty, because you know that you're 95% certain it's really 51 to whatever, and mine mine was 50 or something like that. I'm outside of that range. But if my age is within that confidence interval, you can't say with 95% certainty it's different than the average age for all of the rest of the professors. Make sense? It makes a little bit of sense, at least anyway, right? So, now what about when we get two samples, right? Let's say we get two samples. It gets a little bit trickier. When we get two samples, let's say that group A, group A and group B. And group A, my sample size is 100. And for group A, my sample size is also 100. And X bar is equal to 80. And it turns out my confidence interval, I'm not going to deal with standings, my confidence interval turns out to be 78 to 82. So I am 95% certain, 95% confidence interval, right? I'm 95% certain that the true mean for group A is between 78 and 82. I don't know for sure. I just know I'm 95% certain it's between 78 and 82. Well, how about group B? Say I take another sample size, and this time the mean comes out to be 85. And what I'm really interested in is group A. Is the mean for group A equal to the mean for group B, or is it different than the mean for group B? So let's say my 95% confidence interval for group B turns out to be, let's say 85, turns out to be 83 to 87. Well, they don't overlap, do they? Right? This goes from, I'm 95% sure this one's between 78 and 82, and I'm 95% certain that this one is between 83 and 87. That kind of suggests to you that the real true means are different from one another, rather than if these had overlapped, right, where it had been 81 to 89 or something like that. Then, could have been this low and still be within the confidence, could have been this high. There's a problem with that. We don't do this because there are reasons why mathematically we could be fooled here into thinking that there is no difference when sometimes there is a difference. So we don't do that. However, if we were doing a single sample test, we sampled group A, and we got this result with the confidence interval. And we knew for a fact that we sampled everybody in group B, and we knew that mu was equal to 85, right? Well, in that case, when we're doing single sample test, we can say that if this is our 95% confidence interval for the mean for group A, and I know mu for group B is 85, I know that the mean, true mean for group A is 95% certain to be different than the mean for group B. I can do that with a single sample test, right? Take a look whether or not the mean that I know falls within the confidence interval for the mean of the group that I don't know the true mean for. Okay. So we're going to turn that around now. We're going to turn that into a statistical test called a t-test. You might have, how many of you guys have heard of the t-test before? Yeah, it's come up before, right? It's called a student's t-test because the person that developed it was he used the pseudonym student as his name, and he was working for a brewery. And in a brewery, they were working with relatively small batches, and they needed to know whether or not this particular mix made a higher alcohol content than this one, and they would test small batches, so we only have sample size of 3 or 4 here and 5 or 6 batches here to be able to compare. So he needed a tool to compare average numerical values when the sample sizes were small. So he developed this test called the t-test. The t-test is a method to compare means. That's really what it is. It's comparison of means. Okay, so there's a lot of situations where you could use this t-test. And the situations include number one, where you know a mean, one mean, right? But the other group, right, you don't know, right? So in other words, you take a sample from one population and you compare it to a known mean from another population. That's what we just did with the t-test, right? That's what we did with confidence interval. We're comparing a known value to a sample that we took, confidence interval sample we took. That's called a single sample t-test. Okay, the only problem is that most of the time you have mu1 for group 1, mu2 for group 2, and you don't know either mean. So you have to sample both groups. So this might be males and females, right? So the only thing you know about this group is that X bar 1, S1, X bar 2, and S2. So you have 2 samples. You don't have a single sample. And we just said you really can't use the confidence intervals to see if they overlap or not, because there are issues there with the calculations, right? So you need a different kind. This is a single sample t-test, right? Now for this, you're going to need a 2 sample t-test. You're going to need a version of that test that looks at this without using those overlapping intervals. Yes? I'm sorry, say again.
You're writing S for standard deviation?
Yeah. Yes.
S.
Yep. S or SD. Yes. It's not SE. It's not standard. It's not standard error. It's actually standard deviation of the sample, which is an approximation of the standard deviation of the population, right? So you're going to have instances where you're going to have 2 samples. In fact, 2 samples is going to be more common than a single sample t-test, because usually that's kind of what you're doing. You kind of, like trying to evaluate the performance of a placebo versus a drug, an intervention versus a group that doesn't have the intervention, to see what the result might be. Okay, so the only problem with that is, remember when we talked about X bar plus or minus whatever we're going to use, let's call it T times the standard error. How do we calculate the standard error? We use S over the square root of the sample size. Well, wait a second. We got 2 sample sizes here, and we have 2 S's here, right? Which one do we use? We have to find a way to combine these 2, because otherwise, what would we use one and not the other? Are they the same? Are they different? And so on and so forth. So you can have 2 versions of the 2 sample t-test. One for equal variances and the other for unequal variances. So now we got 3 t-tests. We got a single sample, we got a 2 sample assuming equal variance, and a 2 sample assuming unequal variances. Okay. So, and you want to know something, dirty little secret, we got a 3rd one too. And that's a situation where we're taking the same subject, testing them, and then exposing them to an intervention or some drug or something like that, and then testing them again. So basically, instead of having 10 people in the drug group and 10 people in the placebo group, to 10 different people in the placebo group, in other words, we have 20 pieces of data, we can have a situation where we take subject 1, 2, and 3, and we test their blood pressure before they take the drug, and we take their blood pressure after they take the drug. And we take this other person and take their blood pressure before and their blood pressure after. And another person their blood pressure before and their blood pressure after. Right? Well, in this case, instead of adding all these extra variables, maybe these 10 people are heavier smokers, maybe they weigh more, maybe so on and so forth. Instead of adding all those variables in here, why don't we just take the difference between these two and just look at the differences before and after for the same person? That's called a paired sample t-test. That's called a paired sample test because you're really looking at two pieces of data and you're only interested really in the differences between them, right? So you want to know a dirty little secret. Then we wind up with all the differences, and we can look for the average difference. Okay, if the drug has no effect, and the blood pressure is the same, what would you expect the average difference to be? You expect the average difference to be 0. Sometimes it'll be higher, sometimes lower, but the drug didn't have any effect, so you'd expect the difference to be 0. So what you do there is you calculate your confidence interval for the differences that you measured, right? And it's the point there is it different than 0? So it's a single sample test. Here's your sample result for the different average for the 95% confidence interval for the differences, and here's what you're comparing it to 0. So in this case, you can say with 95% confidence it's different. They're different. But if this were -2 to +5, right? Well, then you're not outside of the confidence. It could be 0 within that confidence, right? So we have four different kinds of tests here that we can do for different kinds of data. And we're going to get started on the first one. Is pretty simple.
The last one called paired.
That's called a paired samples test, yes. Okay, so in this document, I have summarized, the single sample test is really simple. I didn't bother to put it in here, but I've summarized the formulas. Trust me, it looks ugly, but we're going to tame these formulas for you, right? So this is the formulas you would use for a two sample t-test, right? Where we're assuming the variation, the standard deviations of the two samples to be equal. These are formulas for when they're two samples. When they're not equal. This is for proportions. We're not going to worry about that for a couple of weeks. And I think for paired samples, it's just a single sample test, right? Except that you're looking at the differences. So we have some formulas here. They look a little intimidating, but like I said, we're going to wind up taming those quite a bit. Okay, so let's take a look at this first example. Okay, single sample t-test with a known sigma. I'm going to skip that. And the reason why I'm going to skip that is because it almost never happens, right? So I'm going to make that italics. Okay, I'm just going to jump here. Single sample t-test with unknown sigma. You don't know mu, you don't know unknown mu and sigma. I'll put mu and sigma, or not known, right? So you take a sample from population A, and these are the values, 5, 7, 8, 9, and so on and so forth. The sample size is 9, and you don't know what sigma is, right? So we don't know that. All you know is that this is your sample of 9 people. This is the score that they got. Sample size is 9, and you want to test it against a population with a known mean of 8. So we're going to calculate basically a confidence interval for this group of 9, for these 9 values. I'm going to open up Excel. And in fact, if you look into those files that I asked you to download, you can either copy. You don't really have to use those if you don't want to. single sample t-test XLSX. I'm going to open that in Excel, and there are those numbers in Excel, right? So in order to calculate a confidence interval, I need to calculate X bar, whoops, X bar. I need to calculate the standard deviation. I need to calculate the standard error, right? And I know my sample size is equal to 9 here. So that'll help me out. So X bar is the average. S, how do we calculate S? We use equals. So average is going to be what we use here. For S, we're going to use STDEV. For standard error, what is that equal to? That's S over the square root of the sample size. And then my confidence interval. I need to look up what my T critical is. So for how many degrees of freedom would this represent? Sample size of 9? 8, right? I have to look up what T critical is for 8 and 95% confidence. Okay, and then you're going to use that to calculate your standard error, and then you use that to calculate your confidence interval. The upper limit, right? And what is that going to be equal to? That's going to be equal to X bar plus or minus. It's going to be whatever T is for that number of degrees of freedom times the standard error that you calculate. And what we're going to be looking for is whether it's going to be the same or different as mu is equal to 8. Whether or not mu is equal to 8 is within that confidence interval or outside of that confidence interval. Okay, I'm going to leave you guys to do that for 5 minutes. Okay? You can use Excel or you can use a piece of paper. And So is 8 inside the confidence interval or outside? How many found it inside? Outside? No opinions yet? Okay, I'm gonna work on this with you. Okay? So let's give this a try. So X bar is equal to the average of these 9 numbers, which is 9.8888. And the standard deviation of these numbers is equal to, that's the DEV parentheses, it's going to be 2.93, a little less than 3. The standard error is going to be equal to, it's equal to the standard deviation, 2.93. Oh, hang on, before I do that. X bar is the mean for this sample, not for the population. S is the standard deviation for this sample. But like the mean for the sample, it approximates the standard deviation of the population, right? But it's not the standard deviation of the population. It's as close as we can get with this particular sample size. So what is the standard error? It's equal to the standard deviation over, we don't have sigma, so we got to use S, over the square root of the sample size. Sample size is 9, so I'm going to use 3. I'm not going to bother to put square root in, I'll just use 3. It's simple enough. That's my standard error. That's the range. It's basically the standard deviation for repeated samples of size 9. That's our guess based on the sample anyway. Okay, so now let's see. In order to calculate my 95% confidence interval, I need to know X bar, I know that. I need to know plus or minus the standard error times the value for T for 8 degrees of freedom, right? There's 8 degrees of freedom here. So I'm going to go to my T table. Okay, and my T table is aggressively, let me see, I gotta spin this out a little bit. T table is right here. So for 9 degrees of freedom, first 95% confidence interval, notice it says T.025 right tail probability. There's a right tail and a left tail on the normal distribution outside of the area of our 95% confidence, right? So it's giving you half of that. So it's really, you got to consider there's also a left tail. So 95% confident means that you could be off by 2.5%. There's 2.5% likelihood you'd be off You could miss it on the lower end and 2.5 on the upper end. So it really adds up to 5%, hence 95% confidence. So for 8 degrees of freedom, it's 2.306. So I'm going to go back to my calculation, and I'm going to say I'm going to go to this formula, and I'm going to say T, right? T is equal to 2.306. Okay, so what is T times the standard error equal to? Okay, it's going to be equal to 2.306 times my standard error, which is 0.9781. And it comes out to be 2.25. What do we call that value again? You guys remember what we call that value? We have a name for that. It's the amount that we add and subtract. It's the margin of error, right? Margin of error. And we're going to add, add and subtract that from our mean X bar. Yeah, there we go. Okay, so I'm going to add and subtract that. Okay, so it's going to be equal to the X bar minus our margin of error. That's T times the standard error. And it's going to be, and our upper range of our confidence interval is going to be equal to X bar plus our margin of error. Okay, so our 95% confidence interval is 7.6 to 12.1. Can we say with 95% certainty that my mean for the population where I took this sample is different than 8? I can't say that it's different than 8 because 8's within the confidence interval. It could be 8, right? In order to say it's different than the population I'm predicting has a mean of 7.6 to 12, right? In order to say that it's different, I would have to compare it to a number that's less than 7.6 or greater than 12.1 to be 95% certain, right? So if I had said compared to a population that's 7, in that case I could have said I'm 95% sure that my true mean for this population where this sample was drawn from, I'm 95% sure it's different than this population that has a mean of 7, because that 7 is outside of my confidence interval. So that's really how I'm going to use this. This is the way I'm going to do this. Now, if I'm looking at the confidence interval, only problem is it's only going to work for a single sample t-test. So I want to do this in a form that will work for all tests, t-tests, all comparisons to means, 2 samples, and so on and so forth. So I'm going to do this a little bit differently now. I'm going to calculate what is the number of standard errors. What's the t-value? The number of standard errors between the mean that I think I have, X bar, and the mean that I know, that's 7, for instance, or that 8. Right? In this case, I'm going to go back to 8 for right now. How many standard errors apart are they? And how can I calculate the standard errors? Remember how we did that before? We calculated the difference between the 2 values we were interested in to see how many standard errors there were apart, and divided it by the standard deviation, in this case, the standard error. That's how I'm going to figure out what the t-value is for this difference. How many standard errors apart is this? Okay, so before I do this, I'm going to define a t-critical. This is how far apart do these two have to be for a sample size of 9 for me to say that they're different. What do you think the t-critical should be here for a sample size of 9? We already have it on the page here. It's 2.309, right? That's going to be our critical value at t. If we exceed 2.309 for the difference between these 2 means, then we can say with 95% certainty that they're different. Same as we would with the confidence interval. We're using the same t-value and standard error as we're using when we calculate the confidence interval. So in this case, it looks to me, if this is really going to work, that my t-value is going to wind up being less than 2.3. In other words, they're too close for me to say that they're different. So I get the same result as I got when I calculated the confidence interval. Okay, so let's calculate it. So t-critical is going to be 2.306. We got that from the t-table, and that was for degrees of freedom equals 8. Okay, so let's actually calculate. It's equal to It's equal to x bar minus mu, x bar minus mu, which is 8, right? I'm going to put that into parentheses so it does that first, the difference between those, divided by the standard error, which my standard error was calculated to be, where is it? It's right here, okay? And I'm going to hit enter, and it comes out to be, my t value comes out to be 1.93. Is that less than t critical? Yes, it is. So I can't say I'm 95% certain. They're not far enough apart. They're not enough standard deviations apart for me to be 95% certain that the real means of these two populations are different. Well, we're going to formalize this idea of how to do this now. Okay, there's another document on there, and that is called where is it? Okay, it's a TIFF file. It's a picture. Hypothesis tests. State the hypothesis, both null and alternative. Specify the significance level, alpha. Draw a sample of size n. Compute the test statistic. Okay, that's going to be our t-value that we just did. Determine the p-value, the probability that you would be wrong if you reject the null hypothesis, the probability that you would get that big a difference if the means were not different. And compare the p-value to the significance level, your alpha. And what does that mean in English now that I've said all that, right? Let's take a look at this. Okay, so I'm going to go back to my Excel sheet. And the thing I'm going to add on here for starters is before I actually start doing this, let me see if I can't just copy all this, cut all this and move it all down a bit. There we go. Before I even start this, I'm going to say that I'm going to start a null hypothesis. I'm going to call that H null. And my null hypothesis is going to be, let me turn this thing off. Okay, turn this off. My null hypothesis is going to be that mu1, right? It's going to be pretty general. I'm going to use it all the time, is equal to mu2. I'm going to start with the assumption that there's no difference between the two means of the two groups. And then I'm going to want to prove my alternative. My alternative hypothesis, H alternative, is going to be that mu1 is different than mu2. Okay, that's what I want to prove. I want to be able to reject the idea that the two means are equal and accept the idea that the two means are the same. Reject the null hypothesis, accept the alternative hypothesis. Okay, what's the second step there? The second step is I had to establish before I start what level of certainty that I want. Well, up to now, we've been using this term 95% confidence interval. 95% confidence interval is basically the same thing as accepting 5% chance of error, right? That's called, I'm going to call that an alpha error or type 1 error. I'm going to say that alpha, the level of a chance of error that I'm willing to accept is 5%, 0.05. If I wind up with a result that has less than 5% chance of being wrong, well then I will not reject the null hypothesis. I will reject the null hypothesis. If there's more than a 5% chance of being wrong, I'm not going to reject the null hypothesis. I'm going to fail to reject the null hypothesis that they're equal. In this case, we're dealing with a one sample t-test. And our one sample t-test, we know that we're comparing the mean for a population that we have the sample from to a known value of 8. So I'm going to put an 8 over there instead of mu2 because it's a known value. There's no need to say that it's mu2 because we know what it is, and equal to or not equal to 8. So I can use I can phrase my hypothesis that way. I could have left it the way it was before, but I think for a single sample test, this is a little clearer. Okay, so now I go ahead and I calculate how many standard errors apart these are. I calculate my t-score. That's what we just did here. And my t-score came out to be 1.933. The problem is that in order to be 95% sure, to have a less than 5% chance of being wrong and rejecting the null hypothesis, this t-value had to be how big? It had to be 2.306 for this sample size. And I did not exceed, exceed the t-critical, which means my Alpha is more than 5%. I have more than 5% chance of being wrong, right? So I fail to reject my null hypothesis. Had we been comparing it to a value of 7, what would have happened? Value of 7, when I fill this in here, right, this would have been B7 minus 7 instead of 8. Hit enter. And this time I come up with a t-score of 2.95. What's my critical value of t? 2.306. Since my critical value of t is what I have to exceed to have less than 5% chance of being wrong when I reject the null hypothesis, since it's 2.95, what can I say now about my null hypothesis? I can reject it, and I can accept the alternative hypothesis. I'm sorry, say it again. I'm in my head. I'm making them up. Okay, that's the known mean that we're comparing it to. When it was 8, they weren't far enough for me apart for me to reject the null hypothesis. How did I know that? Because my t-value when I calculated based on 8 was not bigger than 2.03. When I did it again with 7 as the known value, I'm comparing my x bar to. Well, then they were further apart, so the top of that fraction was bigger, which meant that my t-value is bigger. It came out to be wherever it went here, 2.995, which is bigger than the critical value that you needed to exceed to reject the null hypothesis. So in this case, I know that my probability of getting this extreme a difference between these two means, I know that my probability of getting this extreme a difference is less than 0.05. How do I know that? It's because the t-critical is exactly a 5% chance of getting this extreme result, of getting it wrong if I reject the null hypothesis. That's 95% confidence. So if I'm more than the t-critical, I know they're further apart than I need, so there's less than 5% chance I would be wrong. And I refer to that as the p-value. When I use the t-test this way with the t-table, all I can tell is that since I exceeded t-critical, the p-value is less than 0.05. I don't know what it actually is. Okay, let's do it again using SPSS. Okay, so if you look at those files, we have an SPSS version of these files, a single sample test.sav. So let's open that up. Yes. Yes, it's the same thing as the t exceeding the t-critical. In other words, the p-value is the probability that you would get that extreme of value if the null hypothesis were true, if the two means were equal. Okay, and since they're further apart than you need them to be to have 5% chance of that happening, since they're further apart, that makes it more certain that the means the two values are different. So it means the probability of being wrong in rejecting the null hypothesis, basically, bad way to phrase it, but I'm gonna leave it at that rather than pound your heads with the way a real biostatistician would phrase this. Okay, but there's less than 5% chance you would be wrong in rejecting the null hypothesis. That's an anathema to a real biostatistician. He wouldn't say it that way. He would say that there's less than 5% chance of getting that extreme a difference in the two means if the null hypothesis were true. Okay. But it's kind of almost like saying the same way, except I think it's more intuitive this way. Less biostatistically correct, but more intuitive, I think. Okay, so we can tell whether or not we can reject a null hypothesis just by seeing if we've exceeded t-critical for that sample size and the difference of the two means. However, it doesn't tell us exactly what the probability of being wrong is, right? Incorrectly rejecting the null hypothesis. That's the p-value. That's the real probability, like the z-score. If the z-score above 1.96, what would it be at 2.3, for instance, the z-value? It would be a much smaller tail at each end if you were looking at 2.3 standard deviations away from the mean, right? The smaller probability, in other words, in the tails. Okay, so SPSS will do this all for us. These are the same numbers that you see before. You could actually go just copy and paste them in here into a blank data sheet. You could have opened them from the Excel file, if you had just those numbers in the Excel file. So I'm going to take a look at these now, and I'm going to run that same test. So I'm going to, actually, before I do that, I'm going to say Analyze, Descriptive Statistics, and I'm going to go into Descriptives. And I'm going to ask it to take that variable X, it happens to call it. I'm going to open up options. I'm going to ask it calculate the mean, the standard deviation, the standard error, and let's see. Okay. The variance, I don't need that. Okay, I'm going to click OK. I'm going to click Continue. And I'm going to say OK. Let's see what it comes up with. Okay. Now, these numbers should look familiar. Sample size is 9, minimum is 5, maximum is 14. The mean is 9.89. The standard error is 0.978. Standard deviation is 2.34. We got that. This is just 2.934, the standard deviation, divided by the square root of the sample size 3. So it got the same numbers we did in descriptive statistics. It didn't calculate a confidence interval, though. I can go back in here to Analyze, Descriptive Statistics. I'm going to move down one to Explore. I'm going to ask it to do the same thing again. I'm going to move it into the dependence list, actually the variable we want to calculate. I'm going to put statistics, and it's going to calculate a lot of the descriptives, and it's also going to calculate the confidence interval for us, a 95%. I could change that to 99 or 90 if I wanted to, or any number I wanted to. I'm going to leave it at 95. I'm going to click OK. SPSS is going to open up the output window again, right? And it's going to give us our results. It's going to give us a lot of stuff. Okay, so let's take a look at the descriptives. Gave us the mean again, gave us the standard error. Look at this, it gave us our confidence interval. It gave us 7.63 to 12.14. So, okay, and gave us a lot of other statistics, gave us a box plot and so on and so forth. But it's the same numbers that we calculated when we did our 95% confidence interval. So we're 95% confident that the true mean for this, the population this sample is drawn from, is between 7.6 and 12.1. So if we're comparing it to a known population with a mean of 8, we can't say with 95% certainty that the mean we took this, that the population we took this from, doesn't have a mean of 8 because it's within the range of our confidence, right? But if we were comparing it to a population that has a known mean of 7, we could say we're 95% sure it's different than the mean for our population, which we're 95% sure is between 7 and 12. 7.6 and 12, right? That's the way we're using this. However, the more proper way to use this is to go ahead and do that t-test. Calculate exactly how many standard errors apart these are. So I'm going to go into Analyze. Surprisingly enough, where are we going to go? We're going to go to Compare Means, right? So SPSS is a pretty intuitive program when you use the drop-down menus, right? So Analyze, Compare Means, and what kind of test are we doing here? Single sample t-test, right? I'm going to click single sample t-test. It's going to come up. It's going to ask me for the test variable. That is, it's going to calculate our mean, confidence interval, and so on and so forth for that variable, for our 9 values, right? So the only thing is now, how do I tell it what to compare it to? What's the mean of the other population to compare it to? Well, I put it in here for the test value. And the test value, I'm going to start out with what we started with, 8, and see what our result is. I'm going to click OK. And it's going to calculate the mean, standard deviation, standard error again, and then it's going to calculate our one sample t-test. And what is the t-value that it finds? It's 1.9 whatever. Same thing we found, right? And what are the degrees of freedom? 8. And what is the significance? What does it mean by significance? SPSS calls the p-value the probability that you would get this extreme a difference between the two means, the one we spar and mu, the one that's known 8, in other words, this extreme of difference with the null hypothesis still being true. In other words, the two means are equal. What's the probability of that happening? Probability of that happening is 9%. That's too high a level of chance of error for us to reject the null hypothesis. What does that have to be less than for us to reject the null hypothesis? 5%, right? 0.05. So there's two clues here that we failed to reject the null hypothesis. One is that the t-score is less than the critical value for t for 8 degrees of freedom. And the other is that our probability of being wrong at rejecting the null hypothesis is 9% instead of 5% or less. Okay. So that's how we do a t-test. That's basically how we do a t-test with a single sample. If I were to do this again, analyze descriptive statistics, analyze, compare means, one sample t-test. I'm going to compare it this time. I'm going to compare it to a mean from a population whose known mean is 7. Okay, what do you think the value of significance is? The p-value is going to be this time. Is it going to be more than 5% or less? You guys know enough to answer this. What do you think? More? There are only two choices, right? 50-50. Give me an answer. You're 50-50. How, you know? I'm going to put in 7. Is the p-value, the significance, going to be less than 5% or more than 5%? Let's say it's going to be. They're going to be. I'm comparing 7 to my confidence interval, right? So they're further apart. So it's less likely I'll be wrong if I say that they're different. So my p-value is going to be less than 5%. Let's say okay, or certainly less than the 9% we saw before. And indeed, the p-value is only 1.8%. It's only 2%. So this is evidence. Look at the t-value. It's 2.9. It's more than the critical value of p, which means that my probability of being wrong if I reject the null hypothesis and say the means are different is less than 5%. In this case, SPSS actually calculates that p-value and lets me know that it's under 2%. Not only is it under 5%, it's actually under 2%. Okay, so this is a lot to swallow in one gulp here, right? Okay, so, all right, let's do another example of this. Okay, except this time, I'm only going to ask you to use SPSS to do it. And I don't really have a second sample set there, so what I'm going to do instead is let's see what's in here. 2 samples. Okay. You know what I'm going to do? There's a data set here called NC birth, right? You see it down there? That's a sample of 800 people in a birth study, 800 births, North Carolina, during a particular year, a number of years ago, and it has the data from those births. I'm going to open that up. I think maybe I should give you guys a break. Right? I see a couple of people getting up and nothing. Why don't you guys take a break for 10 minutes? Okay? Yes.
The question that you just asked.
Yes.
How you feel that if the probability by
If the t-score is, I'm sorry, say it again.
you said that if you went from 8 to 7.
Well, yeah, but remember that the value that, what was X bar? X bar was like 10, right? So if you're comparing 10 to 8, they're close together. So in order for you to say that they're different, it's better if they're further apart, right? So when X bar was 9.8 and I was comparing it to 8, they were too close together for me to say that they were different. But when I went to 7, now they're further apart. So the t-score here was 1.9 when it was 8. When it was 7, when I compared 7 to 9.8, the t-score was 2.9. So they're further apart. I can be more certain when the t-score is bigger, when they're further apart. Well, the probability, the further apart they are, the less likely we would be wrong if we say that they're different. In other words, if the person here, if you are 25 years old and the person here is 50 years old, I can be more certain saying, oh, that person's older than you, right? But if you're 25 and that person's 30, I would have a hard time guessing which person was older. My level of certainty would be lower. So you want the means to be further apart. And as the means go further apart, the probability if you would be wrong if you say that they're different goes down. So when it is far apart, there might be a 50-50 chance, like here, 50-50 chance that I would be wrong. If you were 25, that person was 26, there was a good chance I'd probably be 50-50, right? But as the age difference became bigger, right, I can be more and more certain that I would be right to say that the ages are different, not the same. Right? So that's why that p-value goes down as the two means move apart. I see a question. Somebody's holding a computer there waiting to ask a question. I can tell. I can tell from the posture. First of all, turn that up.
Yeah,
Crank that thing up. I know the battery, right?
Yeah, that's quick. So it's
Oh, let me see what I put there. Okay. Let's see.
I took a screenshot of it.
You can blow that up.
Yeah.
Use your fingers. There you go. Let's see what we got here. X bar minus mu over the standard error. Okay, that's the number. That's the mean. That's the mean of the other population. 8. That's mu is equal to 8.
Okay.
Right. So X bar is the mean for our sample, and mu is the known mean from the other population. Remember, this is a single sample t-test.
Right.
It's two groups. There's really two means. There's a known mean from population B, and our mean from our sample for population A, because we don't know the true mean for population A. That's why it's a single sample. You're comparing the mean that you're getting from your sample to a known value for another population, known mean for another population.
Okay. But when you did it, you got 2.95.
When I got, let's see.
I took a screenshot of it.
Yeah,
So
I think I did remember 2.95 from something. Let me click in there and see where I got that one. Okay, where is 2.95?
Right there.
Yeah, that is after I changed the mu to 7.
Oh, okay.
Right. Okay.
But this is
yeah.
the original one.
When it was 8, this is what I got.
1.93.
So now that's less than t critical, so I can't reject the null hypothesis.
This is still different though.
What's that?
This is 1.7 and that's 1.9.
Let's see. I got D7 minus D8. D7 minus. Did I get the wrong one? No, hang on a second.
Or is it because yours is
Oh no,
rounded?
D7 minus 8. Oh no, mine's not rounded. D7 minus 8. Oops. Let me click back in here. We're looking at that, right?
Yeah.
Let's see what yours is.
Mine is 1.71.
Okay, click in there again so I can see the formula. There you go. That's good. D2, where's D2? D2 is 9.89. You rounded it off, I think.
Yeah.
Okay, over D4. You rounded them off. I think that's what the difference is.
Oh, okay.
Yeah, let me see if I use your numbers, what I get. Equals 9.9 minus 8.
Divided by 0.9.
Whoops. Don't do that. Divided by 0.98. Oh, I still get 9. You got one. How did that happen? Okay, let's see. 9.89. 9.89. Yeah, I wouldn't expect that big a difference, right?
Yeah.
9.89. D2 minus 8. D2 minus 8 over D4. D4, 9.8. Why come out different? What did I just do here? 9.8. 9.89. Why am I getting a different answer than you?
Weird. I don't know.
That's really odd. Yeah, let me do this. Equals 9.89. Oh, wait a second. I'll bet you I think I know what might happen. No parentheses. You're missing the parentheses. You have to put that parentheses in there so it does resolves the
First.
top
Yeah.
first
Okay.
and then divide by the bottom. Yeah, I just put a parentheses up there. We're started to, so.
Okay. All right. Thank you.
No problem.
Thank you so much.
Okay, move this out of the way. Get rid of this now.
This conference will now be recorded.
Yeah, you get that. That's not going to be much good to you. Open up the data set NC birth 800 in SPSS. Okay, you can follow it on the screen or on computers or whatever. This screen behind me is not going to do you much good because it's so faded. And this is data from a study from North Carolina on various statistics regarding births during a particular year. There were probably 50,000 births that year in North Carolina, or maybe more, maybe 100,000. But we only have a sample of 800. That's a really big sample, but it's only a sample. So you will never be able to determine, for instance, the average age of mothers that gave birth in North Carolina during this year from this data, because all you'll ever know is the average age for mothers in this random sample, right? So for instance, if I wanted to do that, I'll do that right now. I can say analyze, descriptive statistics, descriptives, and I can move over the variable MH, in other words, the age of the mother, into the variables box. And I can ask, and I'm going to go into options, I can ask calculate the mean, the standard deviation, the standard error, maybe, say continue and say okay. And I will find that the average age of mothers from this sample, X bar, is equal to 26.92, okay, in North Carolina. That's the average age of mothers in this sample set. Is that the average age of mothers of all the mothers in North Carolina? No, it's only for this sample set. This sample set, if it was really done randomly, really represents pretty close to the average age, or is a good approximation of the average age for the entire population of births that year in North Carolina. And the standard deviation should be at least a reasonable estimate of the standard deviation for the entire group of births, for all of the births that year. But we don't know what the real standard deviation is for the entire population of births, because we'll never, unless we measured every one of them or used every, we had a line for every one of them, we'll never know that. So all we know is this 800. So now, let's say that I was going to ask you, is it the average age, if I told you in New York State, we actually record this data same year for every birth, and I can tell you with 100% certainty that the mean age for mothers in New York City that same year was 27.5. Well, what is the mean age here? 26.92. Can I say with certainty that the age of mothers in New York, the average age of mothers for mothers in New York was different than the average age for North Carolina? Can I say that with certainty? No, because I don't know. I know it with certainty in New York it's 27.5. I don't know what it is with certainty in North Carolina. I only know what the average is for my sample of 800 births. However, based on that sample size, 800, based on the variability of that sample S, based on the mean that I got, 26.92, I can build a confidence interval and see if 27.5 is inside that confidence interval or outside that confidence interval to decide whether they're really different. Well, that's one way to do it. We can't do that with two samples and with paired sample. We can't do that with two samples, equal variances, unequal variances, and so on and so forth. So instead, what I'm going to do is I'm going to do a t-test, that student's t-test on this data. So I'm going to open up a document here. Okay, I'm going to open a little text document, and I'm going to minimize that and make a new one. Okay. So I'm going to say, okay, and what's that? I'm sorry, did I miss something? Okay, I'm going to start with the rules that I made up for doing a t-test. And the first thing I'm going to do when I do a t-test, I'm going to define my null and alternative hypothesis. So my null hypothesis is that the mean for North Carolina is equal to the mean for New York City. And my alternative hypothesis is going to be that the mean for North Carolina is not equal to the mean for New York City. Mean age, right? These are ages we're talking about. The thing is, I know what it is for New York City, don't I? What did I say it was? 27.5, right? And what I say, I'm going to put it here too, 27.5. Okay. The next thing I'm going to do, now that I've established my hypothesis, I'm going to establish the level of error that I'm willing to accept, the amount of error I'm willing to accept. I'm going to call that alpha. And what is alpha typically going to be? If I want to be, usually I want to be 95% certain. So what's the level of error? 0.05. That's the level of error I'm willing to accept. So now I am going to have to calculate, based on what I know from my sample, compare it to my mean, my known mean. I'm going to have to determine whether my sample mean, which was 26.92, is far enough away from 27.5 to have less than 5% chance of being wrong if I reject the null hypothesis. Okay, so how am I going to do that? Well, I'm going to do that by calculating a t-value, right? I'm going to calculate that based on t-value. Okay, and that's going to be equal to the difference in the two means, x bar, minus the known mean for New York City, right, which is 27.5. Notice I'm backtracking and putting that in because I know what it is. And I'm going to take that difference and divide it by the standard error for my sample size of 800. And then I'm going to compare that to t critical. Okay, so what do you think t critical is for a sample size of 800 based on what you've seen from the table? Right? It's going to, well, for 100, it's 1.98. So sample size 800, it's going to be damn close to 1.96, right? So I'm just going to use 1.96, the z value, right, for 95% confidence. So I'm just going to use that. So if my t-value, if the difference between x bar and 27.5 is big enough that t turns out to be more than 1.96, what can I say about my null hypothesis? I can, help me here. If my t-value that I calculate is bigger than my t-critical, I can reject my null hypothesis. Thank you. Right? I can reject it. That means when my t-value is bigger than t-critical, it means that it's going to be less than 5% chance I'd be wrong if I reject my null hypothesis. So I reject my null hypothesis. And I accept my alternative hypothesis that indeed the means for these, the mean ages for mothers in these two places are different. If my t-value is less than 1.96, I fail to reject my null hypothesis. That means my chance of being wrong is more than 5%. How much more? Well, based on what I do here, I can't tell, but SPSS will be able to tell me that. So I'm going to now run this test in SPSS so we can decide whether or not we can reject our null hypothesis or not. Okay, so I'm going to go into SPSS. I'm going to say, let's start out, okay, analyze, descriptive statistics, and let's see, I already did it myself, descriptive statistics, descriptives. Okay, and I already put age of mother in there, and I'll just run it again so you can see it again. And indeed, 26.92, and that's our variability is 6, standard deviation is 6, 2.216 is our standard error. So now let's do our comparison of means, our t-test. Analyze, compare means. What kind of t-test is this? Only one of these is a sample. The other one is a known mean. So it's a single sample t-test. Now, in this case, I'm going to move the age of the mother into the test variable. That's good. So SPSS is going to calculate the mean age for mothers in North Carolina, X bar. And now I want to tell it to compare it to, what I want to compare it to? I want to compare it to the known mean for mothers in New York City, mu for mothers in New York City, which I said was 27.5. Okay, let's click OK and see what we get. The SPSS runs a single sample t-test, and it tells us the t-value is 2.709. Don't worry about the negative or positive. It's just going to change whether you put X bar in front or behind. So it's just the magnitude of the t-value is what you're really interested in. Is 2.709 bigger than our critical value at t? Yeah, it is. What was it again? It was 1.96 because it was such a big sample size, right? Okay, it is. So now, what is the p-value? What's the probability I would be wrong if I reject my null hypothesis since I've exceeded the critical value of t? Probability I would be wrong is less than 5%, right? Because a big t-value, big t difference goes along with a small probability of being wrong. Further apart the means are, less likely you're going to be wrong if you say they're different. Okay, and what does the p-value come out to? Comes out to 0.007, a little under 1%. Anytime you exceed t critical for that degrees of freedom, you are going to have a p-value that's less than 5%. So the t critical and the p-value go together. If I had exactly a t-value of 1.96, what do you think the p-value would have been? It would have been exactly 0.05. Right? See how they go together? T critical actually represents 5% chance of being wrong if you reject the null hypothesis. Same way that it represented the range of 95% certainty for the range of the true mean. So I'm going to ask you guys now to do the same test, except this time do it for, let's see, do it for an average age of 26.5 in New York. Okay, let's say that the mean value for the known mean for New York was 26.5. Okay, do exactly the same test. Okay, and again, you would write this out. This is the way that you would prepare a study. This is the way you would write out. H null hypothesis is equal to the mean for North Carolina, which is unknown. You don't know what that is is equal to 26.5, or the mean for North Carolina is not equal to 26.5. And then you would use SPSS to actually do your calculation.
This conference will now be recorded. This conference will now be recorded.
I just resumed the recording. I'm gonna go back again so you can see it from scratch when you play this back. Okay. Okay, so I'm just gonna go through this quickly again. Analyze, descriptive statistics, explore, because I want to break it up into two groups. I'm gonna move the values into the dependence list. That's going to calculate my means, my two groups, my means for my two groups. I'm going to move gender into the factor list to break them so I get the mean standard deviation separated into the two groups, males and females. My output table comes up, and we can see the means and the standard deviations, 2.10 and 2.739, and 7.56 and 1.94. And I can see from that the standard deviations are not, one is not double what the other is. They're a little bit different, but they're not, one is not double. So I am going to give myself the liberty, since they're not double one is not double the other, to assume equal variances for the two groups. This is not a hard and fast rule. This is just a judgment call, right? If it's double, then I would tell it that then I would deal with unequal variances. SPSS though, SPSS is a workhorse. SPSS moves electrons around. So it's not like it has to spend half hour doing calculations. It's going to do calculations in a split second. It's actually going to do it both ways, assuming equal variances, not assuming equal variances. So I'm going to go ahead now and do my analysis, analyze. I'm going to go to compare means, independent sample t-test. I'm going to move values. Again, I'll go back up again. I'm going to move values into the test variables. That's going to be calculate my means. And I'm going to move gender into the grouping variables. Now, gender, SPSS wants to know what are the actual values I'm looking for here. The reason why it's asking this is because you could have a nominal variable, such as ethnicity, where you could have 7 groups in there. And since the t-test can only compare 2 at a time, 2 means at a time, that gives you the opportunity to say, I want to compare gender 2 to gender 6, or not gender, I mean ethnicity 2 to ethnicity 7, or ethnicity 3 to ethnicity 4. It gives you a chance to tell you that. So you would think, since there's only 2 values here, that SPSS would realize what, I don't need to ask, but unfortunately you have to tell it. So I'm going to put in 1 for females and 2 for males. Continue, and then I'm going to say okay and have it do the operation. Okay, so let's see what we wind up with here. It repeated our descriptive statistics. Got the same thing we got that before. So let's see our t-test. Our t-test, there are actually 2 lines here instead of 1 like we had in the single sample t-test. The top line is what you get if you assume equal variances. Apply the formulas that assume equal variances. The second line is the formulas for what you get if you apply unequal variances. Now, there's no rule that says they have to be different. There could be a lot of reasons why they might be very similar, right? So let's take a look at this. Which of these 2 did I say I was going to apply? Well, since the standard deviations are not, one is not double the other, I'm going to stick with the top line, okay? Now, notice the t-test doesn't start over here. The t-test, I don't know if you can see it on your computers. It's way too faint to see up here, that there's a line there, big line, that separates out these first 2 columns from the actual t-test. So the t-test is 2.184 for 16 degrees of freedom. Remember, we said that the number of degrees of freedom when we deal with t-test that involves equal variances, equal standard deviations. We said it was equal to n1 plus n2 minus 2. So 9 and 9 is 18, minus 2 is 16. That's where that came from. So let's see what our probability of being wrong if we reject the null hypothesis is. It happens to be 0.044. Do I reject the null hypothesis? Is it less than my critical value? Is it less than my alpha, acceptable level of error? What was my acceptable level of error? 5%. What's my actual level of error? 4.4%. Do I reject my null hypothesis and say that they're not equal? Right? Reject the null hypothesis that they're equal, except the alternative hypothesis that the two means for these populations are different. Right? So what other clue would I have had to that? The other clue I would have had to that, if my t-value exceeds critical value of t, or how many degrees of freedom? 16. So I'm willing to bet a paycheck. Anybody wants to put up their paycheck against me? I'm willing to bet my paycheck that that t-value is bigger than the critical value of t for 16 degrees of freedom. Let's look it up. 16 degrees of freedom, it's 2.12. And what do we have here? We had 2.184. Our t-value exceeded the critical value of t, which means that our p-value is going to be less than 5%. So both of those tell you can reject your null hypothesis. You guys okay with that? You guys comfortable? Okay, now, see that bottom line over there? That's what you would have used had you seen that the standard deviation of one group was instead of being close, one was 1.5, and the other was 4, more than double the distance difference. You would have used that bottom line instead. And actually, if you look at that, the numbers are pretty similar. T-value to 3 decimal places, so it's going to be different past 3 decimal places. But look at the p-value, right? A little less certainty there, 0.046, right? Ours was 0.044. A little less certainty. There is an advantage to using equal variances, right? Because you can pool the standard, pool them to get the standard deviation. This would be, you would have rejected the null hypothesis in both cases because they both come out to a p-value of less than 0.05. When I say p-value, I mean the same thing as what SPSS calls significance. Okay, so that's what we have there. Dirty little secret. See these first 2 columns here? That is an actual statistical test for equality of variances, right? See, it gives you a statistic called F, and don't worry, that F, they use that for other statistics as well. So don't think that when you see it again, it's going to be the same statistic. It's a little bit different. Okay, that value of F, that really doesn't mean anything to us, but the significance that goes along with that value does mean something to us. Again, it's a p-value, it's significance or a p-value. What is that? That actually tests whether or not we should assume equal variances or not. Well, now that we've learned a little bit about the null hypothesis, what do you think the null hypothesis for whether or not the variances are equal is going to be? The null hypothesis is that the 2 variances are equal, right? So we're going to stick with that null hypothesis unless the significance is less than 0.05. If the significance for the equality of variance is less than 0.05, we would say reject the idea that they're equal and use the idea that they're not equal, use the bottom row. In this case, even though we use our kind of rough rule, not double, the difference is the standard deviation not double, we wind up with the same conclusion. This is more than 0.05, so we fail to reject the idea that they're equal. So we stick with equal variances and use the top line for the t-value and for the p-value. We get the same result in the long run. We fail to reject in both cases, but sometimes might be a little bit different. Okay, so that is your introduction to your first real statistical test. This t-test, comparison means, you'll find this in abstracts and articles. You'll find this anywhere where people are comparing the means of 2 groups, of 2 numerical variables, the means, and comparing 2 groups. You will find them using the t-test. And what do they say? They'll say that the mean for group 1 was such and such, mean for group 2 was such and such, and the p-value in parentheses equals 0.03, equals 0.06, equals 0.05, and so on and so forth. They'll give you the 2 means, but they will also give you the level of confidence that they have that p-value, so that you can tell whether or not this is 5% chance of being wrong, in which case you might say, well, gee, 1 out of 20 studies like this could be wrong, right? 5% chance of being wrong. Or whether it's like the p-value is 1%, in which case you'd say, well, if they repeated a study 100 times, maybe once it would be, I'd get a wrong result like this, right? This would be a wrong result 1% of the time. So it gives you a little perspective on how good the result is. Also, it means that, if like the other test we got where it was the p-value was 0.55, which suggests that, gee, you probably, are justified in rejecting the null hypothesis, but not, instead of saying you reject the null hypothesis, you'd show the difference in the means with a p-value equal to 0.55. And somebody else would be able to read that and say, well, that's close enough for me. That's good enough for me.